Where does it occur in certain interval of time? It occurs in the area of it. So when it resists a high amount of flow of charges in a circuit, the damages happen is less. How much ever current comes towards the junction, it is said to be zero. Hello everyone, I'm Brinda, Faculty of Physics, welcoming you all to the session 1 of chapter 3, and chapter name is Current Electricity. In today's chapter, we are going on to the master chapter wherein you will have to know few of the important concepts. So let us discuss on those things. So now we have Ohm's law. So current electricity means the generation of a current due to the charges, and the charges are said to be electrons. So electrons hold or play an important role in terms of this generation of electric current. So as you all have studied in your first chapters and all, you know how exactly the flow of charges takes place, how exactly the field and all takes place. So with respect to that, in the second chapter, that is with respect to the potential, wherever there is a current, there is a potential. So it is directly proportional. So with respect to that, we study Ohm's law. What is Ohm's law first of all? The potential difference which is applied across the conductor. Suppose if this is a conductor, and the potential difference which is applied across the conductor, it is directly proportional to the current passing through it. So we have potential is directly proportional to the current passing through it, which current is given in terms of I. So proportionality constant is removed. So we have something which comes there. So that is R, where R is known as a resistance, which means to say V is directly proportional to I. V is equal to I into R. So this concept is known as Ohm's law. So where the SI unit of potential is volts, the unit of resistance is ohm, the unit of current is coulomb. So that's all about your Ohm's law concept. Having this concept, moving further, resistance dependence on where and all it is dependent. So resistance is nothing but it resists the flow of what is its uses in order to resist the flow of charges in a circuit. So when it resists a high amount of flow of charges in a circuit, the damages happen is less. So on what it depends? It depends on the what type of material you use. It depends on the temperature. It depends on the dimensions of the conductor, like length, breadth and all those stuff. So according to certain set of law, resistance is directly proportional to the length and it is inversely proportional to area of a conductor. Again, on removing its proportionality constant, we have a rho L by A. This rho is also called as resistivity. So how can you define the resistivity? With the help of this formula as rho is equal to R into A by L. Okay. So this is the equation. So now resistivity is directly proportional to resistance, directly proportional to area, but inversely proportional to length, wherein it is in different case in case of the resistance. Next we are going on to drift velocity. That is, the velocity means about your electrons or the charges which gets drifted. So the average velocity with which the free electrons get drifted. So always the electric field, the drift velocity is always opposite to that of an electric field, wherein drift velocity is given in terms of Vd. Drift and velocity. Vd is the notation. So as there is a presence of external electric field, the electrons, the free electrons get drifted opposite to that of the field is what you will have to consider. And next we just check on to the relation between current and drift velocity. So what is current? It is given in terms of I. How is drift velocity given? Vd. So these two are the conditions for which we know that consider that there is a conductor of certain length L. So certain area of cross section A, and there is a electric field which is moving here. So the electrons is getting drifted in the free electrons are getting drifted in the opposite direction of the field. That is what you will have to know. Okay. So when these are the conditions what we have, these are the set of conditions we have. we have to start up with consider there is a conductor, certain length L, through which a potential is being passing. So the field, electric field is given by V by L. The potential with respect to the dimension of it. E is equal to V by L. So this is the equation what we actually considered for the presence of electric current with respect to potential as well as its dimension. Now let us start with, as there is an electric field which is produced and there is a drift velocity for the free electrons in opposite direction, we have Vd. This is a drift velocity. And this drift velocity is undertaken or it occurs in certain interval of time. So we have Vd into delta t. Where does it occur in certain interval of time? It occurs in the area of it. So we can write it as Vd into A into delta t. And in that area, how many number of electrons are having this drift velocity? It is n number of electrons are having the drift velocity Vd into delta t. So n number of what is having? That is electrons is having this drift velocity. Okay. So this concept is nothing but the charges which is flowing in this conductor. So it can be given as delta Q is equal to NEA Vd into delta T. As you all know, we have to equate with respect to current. We have got Vd here finally and there is no current I. Anything with respect to this we can't equate. So let us go to the left hand side. So current I is equal to charge per unit time. So I can rewrite this as Q is equal to I into T. So I into, since there is charge, I can write it as delta T is equal to NEA Vd into delta T. Delta T cancels with delta T. So we have I is equal to NEA Vd. So this is the concept what we have, and this is one of the important equation as well as the derivation for your next set of any numerical sort or any objective types which is higher level. For all those things, this is very, very important derivation as well as the equation. You should always remember the final equations in CBSE class 12. So here we have relation between current and drift velocity. We have a current here, we have a drift velocity here. So it's clear. Okay. So next let us go to temperature dependence of the resistivity. How the temperature depends on the resistivity components. So in case of metals, if you have resistivity and temperature, it's always as the temperature increases, the resistivity of the metal also increases. In case of your semiconductors, with respect to resistivity and temperature, as your temperature increases, the resistivity decreases. Likewise, in a different case, in case of alloys, you have as the temperature increases, the resistivity increases, but from certain level, that is this level. Okay. So this is how actually we study. We have to know about the temperature dependence of resistivity. And next we are going to Kirchhoff's law. These are one of the most important laws for the upcoming concepts like Wheatstone's network. That Wheatstone's network, you use it in meter bridge concepts and all in your practical exams. So that is how exactly it goes. So two types of Kirchhoff's laws are there. One is Kirchhoff's first law and second law, Kirchhoff's junction rule. And this is, or it is also called as current rule. And this is second law is called as Kirchhoff's loop rule, or it is also called as voltage rule. So that's all about your Kirchhoff's two types of rules. So let us know what exactly is this junction rule or the current rule. The first KCL, Kirchhoff's current law. So it states that in a closed electrical network, that is completely closed electrical network, whatever comes in to the junction if suppose I1, I2, I3, everything, whatever comes, I current comes here, everything is said to be zero. In a closed electrical network, the algebraic sum of current meeting in a junction is said to be 0. Okay, this is one of the important law that is called as current rule. How much ever current comes towards the junction, it is said to be 0. Okay, so how about your Kirchhoff's voltage rule, or it is also called as loop rule? This is also one of the important concept. Here it says that the algebraic sum of potential that which change in potential as well as the EMF around the closed network is said to be 0. The same thing goes with KVL also. So you have to remember what is KCL, what is KVL. So you need to understand this and go further with respect to Wheatstone's network. So you have balancing condition of Wheatstone's network. So let us see what exactly we are doing here. We have a circuit, called it as Wheatstone's network, and we have EMF as well as the key. The current flows from here and branches out and joins here. Again, the branching comes here to I3 and I4 and finally moves to a negative direction or a negative EMF. So to have this, let us just work it on that. That is PQRS are the resistance of this bridge. So there is a I1 current passing, I2 current passing, I3 as well as I4 current passing. So the direction is given here and we have a G here. That means to say there is a current which passes from G also, and you can call it as IG, and there is a other current which passes through I4 and it moves here in this manner. This is the direction. So we have I1 here direction, I2 direction, I3 direction as well as I4 direction, which is mentioned over here. So this is what you have to keep it in your mind first. So we have P, Q, R as well as S. These four are the set of resistance, and there is a galvanometer which has IG, and the movement of the current through a galvanometer is shown in case of your arrow marks. And these are the components, these are the junctions, that is A junction, C junction, B and D junction. For this we have to use Kirchhoff's voltage rule as well as Kirchhoff's current law. Two rules also you're supposed to use. First of all, we will deal with Kirchhoff's current rule. So first of all, keeping the same concept in our mind, we'll have to draw it back again. So we have EMF, we have a key, we have one set, second set, third set and fourth set. So this is how the connectivity goes. A, we have B, C and D. We have a galvanometer, G, from which IG is passing. Arrow marks are shown in this manner. This is I1, this is I2, this is I3. We call this as IG. Let this be I2 and let this be I4, and the arrow comes out to be in this manner. So first of all, applying KCL. First concept is apply KCL to this. So anything which meets at a node is said to be 0. So now the nodes are B as well as D are the nodes to us. Remember, I1 is moving towards the node. I2 is, that is IG is away from the node. I3, we have three concepts. I1 is towards B, IG is away, I3 is away. So by applying KCL, we have at node B, we have I1, this is I1. I1, since it is moving towards the node B, it is plus. IG and I3 are moving away from B, so it is minus. Minus IG minus I3 is equal to 0. We'll equate for I3. I3 is equal to I1 minus IG. So let me call this equation as equation 1. Next our section is D, this point. So in order to derive for it, we have, this is D. So there is I2 which comes, IG which is coming, I4 which is going. This is going, this is coming, this is coming. So point D. For the second point, if we just check, applying KCL at node D, we have I2 plus I2 plus Ig minus I4 is equal to 0. Equating for I4 is equal to I2 plus Ig. Okay, is equal to 0 means according to your KCL. So KCL is over. Now we have to check on with Kirchhoff's voltage rule because node conditions are over. Now we have to take loop conditions, loop rules. So let us just go on with KVL. Applying KVL to first loop. So first loop we have this set Ig, I1 and I2. Let us take it in this condition, that is cyclic or a clockwise direction, or you can even consider anti-clockwise direction. It's left to you how exactly you consider. So here we are supposed to consider the EMFs as well as the potential. So I is equal to, we have V is equal to I into R. So there is a current also, there is a resistance R also in that according to Ohm's law. That is V is equal to I into R. I can be I1, I2, I3, I4, Ig. R can be P, Q, R, whatever is present over here. That is P, Q, R and yes. R and yes. This is how exactly it is. For which we have, first of all, if we just go with I1 current, we have cyclic order wise. So I1, P and plus cyclockwise if we just go, we have IGG. And anti-clockwise, the one which is coming is minus I2R is equal to 0. So now, second set, applying KVL to second loop. If we apply KVL to second loop, we have I3Q, because again we are taking out to be a clockwise, I3Q plus I3Q minus I4 yes minus IGG is equal to 0. So this is the condition. Suppose the concept is balancing condition of Wheatstone's network. In case of meter bridge, when you used to get the balancing condition, whenever the galvanometer used to show 0 condition. So your galvanometer Ig, the current through a galvanometer should be 0. Then only you can say it is in a balancing condition. So wherever you have Ig, you have to put it 0. So first equation turns out to be I1P plus minus I2R is equal to 0. Let me consider this. If this is equation 1 and this is equation 2, let this be equation 3. Next, considering this equation, again when balancing condition is 0, I3Q is minus I4S is equal to 0. This is also fine. Next, substituting for I4 as well as I3. Here you have I3 is nothing but I1 minus I1Q minus IGQ minus I4 is nothing but I2S plus IGS. So again IG, this also goes, this also goes. So what remains is I1Q minus I2S is equal to 0. Let me consider this equation as equation 4 now. Okay, so we have equation 3 and equation 4. On continued, you have these set of questions. So on equating 3 and 4, I1P minus I2R dividing it by I1Q minus I2S equated to is equal to, take minus towards, that is these two set towards other side, I1, I2, I2 cancel. So balancing condition turns out to be P by Q is equal to R by S. This is the final set of equation. This is known as balancing condition of Wheatstone's network, which is very important with respect to numericals as well as the derivations. So now in today's class, we have dealt with the current electricity chapters and important concepts of it. So let us all meet in our next upcoming session. Until then, have a good day. Thank you.